says it's not available. I thought I had opened it up already. Oh, it probably opens up after this class, but I'll double check right now. Options. Okay. It should be open shortly because it says it's display after 1:24 and today is the 24th after 9 a.m. So it should be open and it's due on 1/26 and it's in Blackboard. So it's not on WebAssign, it's in Blackboard. And I got the raw video from Monday up already. So we're going to start. I promised that we would do a pendulum today, so I just want to get the slides up just so that we have the slides so we can look at it and look at where we're at. So current view, let's go from beginning. So remember that we have our motion equations for simple harmonic motion, that anytime I'm looking at a position X, I can look at it in terms of its amplitude and its frequency and the cosine, omega t. So for those of you who walked in late, because when you're writing your phase equation for your simple harmonic motion problem, you get to pick where you start. So you don't have to worry about a phase angle because you get to pick where you start. So so you can start when the phase angle is equal to 0. So that's up to you how you want to deal with that. When I do velocity, it's 2 pi times the frequency, or my omega, my angular frequency, times the amplitude times the sine. And I get that negative because it's coming from the sine. And then I get my acceleration, and I have that equation of motion for acceleration. So we had kind of talked about those equations of motion. So when you're working on your homework, this is part of some of the information that you kind of have in order to get things going. So back on Friday of last week, we kind of went through looking at the pendulum. And one of the things that we were looking at is what was the restoring force of that pendulum. If the restoring force is going to be gravity, it's going to cause me to swing. I have conservation of energy, okay? So when I'm up at the top of that swing and I come down to the bottom, I'm conserving energy. The top of the swing has mgh, it's got potential energy. The bottom of the swing, it's totally kinetic energy. And then it's going to swing back up and it'll go back and forth until friction and air resistance stops it. So I do get dampening. So if I look at the distance traveled of my bob at the end of the pendulum, if I look at that distance traveled, I'm going to go through an arc. And that arc is going to be related to the angle and the length of my pendulum. And I can look at it in terms of the sine, but as long as I stay with a very, very small angle, I can approximate the sine of the angle as actually equaling the angle. So I can keep that very, very small, and then we can put the force that's restoring it in terms of the legs of the triangle, the distance of that curve, and the length of my pendulum. So we can actually look at it that way. And we've done this before. If I put this in terms of Hooke's law, this is going to allow me to rewrite and solve for my essential spring constant. So the pendulum will actually have a spring constant. We can look at the angular frequency that relates to the mass. And then ultimately we can come back and look at the period. But when I put in the period, okay, so I got 2 pi over the period, or 2 pi times the frequency, but remember the frequency and the period are related, and that equals the square root of k over m. But now I've got the k in terms of the mass and gravity and the length, and when I plug that into the equation, it doesn't matter what the mass of my pendulum is. Okay, it doesn't matter what the mass of the bob of the pendulum is, and I can look at the square root of gravity divided by the length, and I can actually measure the period, and I can measure the length, and I can actually measure gravity using a pendulum. So there's my period if I flip it over, because the period will be the easy thing for us to measure, and I've got my length and gravity. So we're going to determine the average period. So I need somebody in here to set up a timer on your phone, because I'm going to switch over and we're actually going to do it. We're going to count the time that it takes to make 10 complete cycles of the pendulum. And we're going to do it 3 times to get the average. Okay? So somebody get ready to be the timer. Somebody get ready to write down the data. All right, so I've got it set up. I have my handy dandy meter stick. Let's see if we can get it in here. I got my handy dandy meter stick. Now, each of the red items on here, each of my red items is 10 centimeters, so you guys can see it on the camera that it's 10 centimeters. So I'm going to go to where the center of mass of my plumb bob is, and then I'm going to use a 70 centimeter pendulum. So my length is 70 centimeters, okay? My length is 70 centimeters. That's where I'm starting from. So I'm going to wrap this up so I can not give it away. All right, so somebody got a timer?
Got it.
You got it?
Mm-hmm.
All right, I want to keep the angle small, and we're going to count for 10 complete cycles. So we're going to count off of this cycle. Okay, ready? 1. Oops, I'm going to have to go longer. Stop. Got to go longer. Let's see what I got. I use up here. That's 120 centimeters. So I've got a 1.2 meter pendulum now. Okay, ready? Trying to, so we can watch it. See if I can see it all the way to the bottom. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What was the time?
21 seconds.
All right, so I'm gonna write that down. So we got 21 seconds for the period for the first time. We're gonna do it 2 more times here. All right. Ready? 1, 2, 3, 4. Ooh, we got damping. Let's do it for 5. We'll just have to, the next 2 we'll just do it for 5. So we'll just have to divide by 5 rather than divide by 10. Ready?
Mm-hmm.
1, 2, 3, 4, 5. What do we get?
10 seconds.
Okay, good. All right, one more time. Okay, I gotta start counting. All right, we ready, Monica?
Yep.
All right. 1, 2, 3, 4, 5. What do we get?
10 seconds.
10 seconds, cool. So I'm gonna switch over here. Maybe. Okay, we're on. Teacher camera, let's see if I can do this. Alright, there we go, back to the camera. This is entertaining. Alright, already dilute. No, I got Enid still here, that's good. And Enid still there. Switch view. No, that's not what I want. Okay, so I'm gonna go back to the computer, see if I can get that back there. I got the computer back. All right, got the computer back. Now let's go to the document camera and see if I can get that. Okay, well then, all right. We'll do it this way. Life is entertaining. entertaining, there's always more than one way to skin a cat. So. We'll do it on Excel. And I'm gonna see if I'm gonna see if I can do this. A little bit bigger. All right, so we had 21 seconds for 10. This one had 10. This is the number. This is the number of cycles. And this is the time, and that was in seconds. So this will give me the period. And when I do the period, I'm going to take the time divided by the cycles. So the period was 2.1 seconds. The second time we did 5, the third time we did 5, and now I've got 10, and I've got 10. And now if I do this and I do control down, that gives us our 3 times that we had. So now I want to do the average, and if anybody's ever seen how to do the average on, if I do an average, I can do the average right there. Oops. I want the average. And then I just put in the range of numbers that I have. So that's how you do an average on Excel. And so there's our average period that we have for the pendulum. That's our average period. Now if I go back to the presentation, I want to take the period divided by 2 pi. I'm actually going to go one slide more. They're solving for gravity. Gravity is going to be 4 pi squared times the length divided by the period squared. So I can actually do that in Excel. So if I do that, I can do 4 times 3.14 times 3.14 times my length, and my length was 1.2 meters. It was 120 centimeters. Divided by my 2.03 times my 2.03. And that gave us 11 meters per second. And we know gravity, because we've been doing it, 9.8 meters per second. So we were off a little bit, but there's a lot of places we could have been off. The place that's probably the most critical in this one is the fact that I kind of rough estimated the measurement of my pendulum length. So if I change my pendulum length, and let's say if I was off on my pendulum length and it really was, instead of 1.2 meters, it really was 1.3 meters, then I'm really off. But if I'm on the other direction and say it was actually 1.1 meters, I'm getting closer. So one of the places I have errors in my length measurement. The other place we had errors, we saw dampening, right? We saw dampening of that pendulum. It started to go slower and slower and slower. So we're probably off in both places. We're probably off in the period and in the dampening, or very off in the period and in the length. But for a rough estimate of gravity, doing it really, really quick and dirty right here in the room, we did pretty good. Yeah, we did pretty good. So that's how you can measure with the pendulum, going back. So I want to go from a different slide. So we can actually do measuring the pendulum back and forth. And actually, if you do really long pendulums and look at that small distance and keep that small angle, you can get really, really accurate with a pendulum. So you can actually get that. So we can actually do that piece. So let's kind of go back and talk about waves, because that's where we were starting from. We talked about on Monday, right, that if we have 2 types of waves, we're going to have transverse and longitudinal waves. We have superposition, where we can add the waves together. And mechanical waves, one of the keys is it has to have some kind of medium. We have to have some kind of medium, and that is being disturbed. So it could be water, it could be tabletops, could be a variety of different things. But we have to have something for that wave to propagate. Electromagnetic waves, we don't. We don't have to have that piece there. So for mechanical waves, we have to have a source of the disturbance, we have to have a medium, and we have to have some physical mechanism through which the elements of the medium can influence each other. So that means collisions, primarily, changes in pressure, that's what we get when we talk about a longitudinal wave, and we can move on from that. So that's where we were on Monday. We talked about a pulse. If I send a pulse down the stream, I can get that string. The string has to be under tension, because if I don't have it under tension, that pulse isn't going to impact each other. Now, if I can take that bump, I can send that bump through the medium. Now, if I look at this, this is one of the places why we start with simple harmonic motion and look at that wave equation. So the pulse is a transverse wave. We see that vertical displacement back and forth. But look at what happens with the motion of this point on the string. As the pulse goes through it, this point is going to move up and down, very much like in that simple harmonic motion that we saw with our spring or with the pendulum or with a number of other things. We'll see this point move up and down as the wave travels through it. Think about a bobber in the lake. When the wave comes through the bobber stays put pretty much, at least in its X position, but it'll move up and it'll move down in its Y position. So we can actually look at those pieces as we have the wave propagate. So we talked about a longitudinal wave, and I used my slinky to demonstrate that longitudinal wave, that we see the area of rarefication. Rarefication means my density is going to get thinner, and compression is where my density gets thicker. So I'm going to get those pieces, and so this will actually get a displacement of the coils as it moves through, and I can look at that particular pulse as it goes back and forth. And we did that with the slinky on Monday. But I can also have very complex waves. I can have combinations. I can have combinations of transverse waves and longitudinal waves. I can have multiple transverse waves. I can have multiple longitudinal waves. And we get a bunch of different things that are happening as we have a wave go through. So we can exhibit both. And surface water waves are an example. The elements of the surface moves in nearly circular paths, and the disturbance is both longitudinal and transverse. Another example is earthquakes. Okay, another example is earthquakes. When we feel an earthquake, if you happen to be out in the pasture when the earthquake occurred, that was in Pawnee. In fact, I had one of my concepts of physics students was actually out bird hunting that morning when we had that really good earthquake. And he said he sat there and he watched the barbed wire fence go up and down. You could actually see the wave travel along the barbed wire fence. You could see that nice transverse wave. That actually is what we call an S wave in earthquakes, and it's a secondary wave. It actually is a little bit slower. But a lot of times we feel that bump. You know, you'll feel that really bump like somebody's hit the house. You know, they'll have that bump that's out there, and that's our primary wave, and those are longitudinal waves that are being transmitted through the earthquake. So the seismograph can record both the longitudinal and the transverse waves. And by knowing which one we have, because they travel at different speeds, we can actually pinpoint where the earthquake started. So you can actually get that pinpoint, you know, dead on where the earthquake starts. So we can actually look at those different waves. And depending upon where you are, you can actually see the damage associated with the two types of waves. In the 70s, Mexico City had a really bad earthquake. Mexico City is on an old lake bed, so when the earthquake occurred, it kind of does they do that liquefying of the sand in the area, and any place where they had the crest of the wave, that's where they had damage. Any place where they were in a node of the wave, they didn't have damage. So you could actually see the damage in terms of concentric rings around that Mexico City earthquake. Similarly, one of the earthquakes in California had something similar happen because the earthquake went from the fault line to the mountains and then reflected off the mountains and came back. And any place where they had constructive interference, they had more damage than if they had destructive interference where they didn't have any damage. And you can actually see it from an aerial photograph. And I've been trying to find those aerial photographs, and I haven't found them in a while. So, but those are kind of fun pieces. So not only can we look at waves as they travel through time, we can actually look at the wave as it's traveling through the medium. So we can look at the wave in terms of its position through the medium as well as its time, and we can look at the shape. So if I take that traveling pulse at time as t is equal to 0, so I've got my pulse, I've got something that drives it, and I get it through the system, I can look at the motion of p as the wave travels through. So I can look at that motion of p as the wave travels through. So if I do that, we can actually look at its vertical position is now in terms of x, where I'm at, and the velocity of the wave times time. So I can actually look at that in terms of my vertical position and time, and I can rewrite my wave equation just a little bit, and this gives us something that we call the wave function, which is going to give me both position and time. And if the time is fixed and we see that picture of the wave, that's called the waveform. So if I have a nice sinusoidal pattern, I get that nice curve, that gives me my waveform. And if any of you have ever seen an oscilloscope, I can change these waveforms. I can make them squares, I can make them different kinds of peaks, I can make them different kinds of valleys, I can make them really sharp. I can do a lot of different things on the waveform. So I can have a wave function and the waveform. And if you think about it from a medical standpoint, when I'm looking at an EKG, an electrocardiogram, we see that pulse, right? We see the pulse of the heartbeat, but it's not uniform. It's not a single pulse. We get a couple of pulses. And we get that jagged response, and that's the waveform that we see from our heart. We'll actually see that waveform. So we can actually look at simplifying the model. It allows us to do more analysis of waves. You guys in this physics class aren't going to do a whole lot more with these waveforms, but I want to show you those so that you have it both in terms of position and in terms of time, so that you see both and we have that traveling wave, because an EKG is very much like that. So here's our more generalized waveform, our wave equation. It's going to give us both position and time. And now we bring back in, here's my x position. So now I have in terms of the spring constant in x. And here is my omega in terms of time. So I have it both position and time. So I can look at it both places. I can still read the amplitude right off of the graph. I can still read the angular frequency right off the graph. But I'm going to need a little bit more information to deal with my spring constant. But I can write those things right out and do both. So we can look at this time when we deal with our angular wave or our spring constant, we can relate it back to wavelength. So I can read that K off of there. That's why I said we need a little bit more information, and wavelength gives us that little bit more information. So we could do the angular frequency just like we did before, and now we can look at the velocity just like we did before. So we can actually do quite a bit with those pieces, and we know the phase constants there. So we can see the same types of wave equations. So when we do sinusoidal waves on a string, we're going to have to do some sort of driver, something that's going to actually drive us. And it'll give us our consistent waveforms as we get it pulsing through. This becomes important when we start moving into sound, because what we're going to do is we're going to look at how a string on a guitar will get us that sound wave, how we get that motion back and forth, and how we get those places where we're going to get a standing wave, where we're actually going to see the antinodes and the nodes. And in order to get music out of an organ pipe, I have to create a standing wave. And I'm going to be able to get those motion pieces back and forth. So we want to look at those pieces. So we look at each element of that string, and each element of the string is going to move up and down according to the wave equation. We just have a much more complex motion. So where we looked at it originally as a mass on a spring, now we're looking at each individual incremental element of my string or my medium. We can actually see that wave moving through. And that's where I'm gonna stop today, because I wanna get us going back into the Doppler effect and start to sound on Friday. So questions about where we're at? You guys have your simple harmonic motion problem is due Friday, and we will go from there. And I'll be in Enid on Friday. Hopefully we will not have too bad of a Friday time in here on Friday.
And the quiz is due Friday.
Quiz is due Friday. Quiz is on Blackboard, quiz is due Friday. I think we've got some homework due Friday too. It's either Friday or Monday, I can't remember.